Hello, I'm Dr. Sham Rane. I'm a senior research fellow at the Center for Compressor Technology. Welcome to this week's Lecture Tuesday. Today we are discussing on an interesting topic of conjugate heat transfer in compressors and its modeling aspects. The word conjugate has a technical meaning of being coupled, connected, or related. When we apply that to heat transfer, it's called conjugate heat transfer, also commonly abbreviated as CHT. And this means coupling of conduction and convection modes of heat transfer in the governing equation of conservation of energy across fluids and solids in our model. Here you can see a layout of such a problem where we have fluid A, which is enveloping two solids, solid A and solid B. And for heat transfer to happen between them, there are fluid A to solid B interfaces and similarly solid A to solid B interfaces. Across this interface, according to conservation of energy, the flux going in and out of the object or body should be balanced. The application of CHT in compressors is far. We take an example of a Howden API 619 oil-free screw compressor here. In the layout, you can see the main housing, which envelopes the two rotors. The visible is the main rotor. What you can also notice is that in the housing there is cooling jacket. Because this is an oil-free compressor, during compression there is high temperature rise. The gas can be compressed up to discharge pressure of 46 bar or with a 15 bar differential pressure in this unit. And the flow is also high, which can be up to 92,000 meter cube per hour. The designed operating temperature is in the range of 150 to 225 degrees Celsius in controlled conditions. Conjugate heat transfer modeling. In compressors, heat transfer from solids to the fluid flow is generally using a 3D numerical approach, which can be in the form of computational fluid dynamics. They can be broadly classified as non-CHT problems or CHT problems. For a model to be in the category of non-conjugate heat transfer, there will still be boundary conditions that need to be applied. And based on the boundary conditions, they can be further classified as adiabatic, which simulates insulated boundaries. On the other hand, when you model conjugate heat transfer, one advantage that you see is that some of these assumptions are no longer required because the model accounts for the heat flux balance between the fluid and the solid. Based on the solver that is used, you can have the whole problem formulated within the finite volume method solver. So CFD model is used for both the fluid as well as solid. Or you can have a coupling algorithm where finite volume methods interact closely with finite element solvers for the conduction part of the solids. Current state of the art uses either adiabatic or finite volume method based conjugate heat transfer most commonly for twin screw compressors. Like every other model, conjugate heat transfer also has its challenge. I will cover the most commonly faced three challenges. The first out of them is the grid at the fluid-solid interface. The first image here represents the solid, the fluid, and the interface between them. And you can notice that there is a one-to-one node connectivity between the two. This is a very ideal scenario because the area of each cell face is equal on both sides. Hence, the flux can be directly transferred from the solid to the fluid and vice versa. However, in reality, the fluid side mesh is generally very refined in order to capture velocity gradients and boundary layer flow, whereas on the solid it is much more coarse. And this difference in sizing results in an interface which is non-conformal. That is, there is no one-to-one node connectivity. In this case, special techniques are required in order to balance the flux between the fluid and the solid, and to ensure conservation. Apart from these basic issues, the geometry is not always flat or simple due to curvature effects and coarsening of the boundaries after discretization. You can either face overlapping cells or gap between the domains. Apart from that, you also have an issue related to heat flux balance. In order for the positive Q to match with the negative Q, every time step has to have an internal tight coupling between the two sides. Either it can be fluid to solid or between two solids. And sometimes this tight coupling becomes challenging because the information is not available. So many solvers use a weak coupling in a form of inner iterations, where temperature from the solid is first implied as a boundary condition to the fluid. The resultant flux is then implied as a boundary condition to the solid, and by converging within an inner iteration, a final heat flux is then balanced to march in the time step. This requires special treatment in the solvers. Another physical effect that is challenging in conjugate heat transfer is when you have a transient flow, as commonly seen in compressors. In this animation, you can see two surfaces. One corresponds to the fluid side temperature and the other corresponds to the solid side temperature. A noticeable difference is seen, although the positions are synchronized, but the temperature of the gas and the solid is largely different. This happens due to thermal timescale disparity, which means that in the fluid flow, the convection of heat is quite fast, whereas it takes a lot of time for that heat to conduct within the solids. This manifests into a different time step size for the fluid solver and the different time step size for the solid solver, which is also known as time scaling. Here I'll show you an example of conjugate heat transfer in an oil-injected screw compressor. The tests were conducted at City St George's University of London's test rig. You can see the image of the compressor on the rig here, and adjacent to that is the electrical motor which is powering the compressor. A thermal camera was used to get the surface data of temperature while a steady operating condition was achieved. This is the thermal image. From this image, we can see that over the housing of the compressor, the temperature varies from about 20 to 70 degrees Celsius during a specified operating condition. The conjugate heat transfer was fully constructed using non-conformal type of interface in a CFD solver, and by investigating the external temperature of this machine, you can see that it is closely in the expected temperature range as seen by the thermal image. To look into the basic governing equations, you can refer to Fundamentals of Heat and Mass Transfer by Incorpora and David. Whereas the numerical side of conjugate heat transfer with some fundamentals and recent progresses can be found in Advances in Heat Transfer. With this, I would like to conclude today's short lecture. Please feel free to get in touch for any further queries or discussion that you may want to conduct.